This video is on nucleophilic substitution. And our aims for this video, firstly, are to be able to draw the mechanism for the nucleophilic substitution reactions using the cyanide ion and the hydroxide ion as nucleophiles. Draw the mechanism for the nucleophilic substitution reaction using ammonia, which is slightly more complicated than these ones, but they're very similar, and explain the trend in the rate of hydrolysis of carbon-halogen bonds. So firstly, nucleophilic substitution will occur between a haloalkane, so that means an alkane that has a halogen attached to it. So let's use bromoethane, but that bromo could be a chloro, could be an iodo, could be a fluoro. But this is generally what you'll see in an exam. And a nucleophile. A nucleophile is something that will seek out and attack positive charged areas. And this compound here has a positively charged area. This bromide, or the bromine atom, is delta negative, and this carbon atom is delta positive in this bond. This bond has a dipole. And if we start with the cyanide ion, which is Cn-. Now, in an exam, they'll often give you a reagent of KCN or HCN, and that's because you can't get a bottle of just Cn- ions. If they ask for the reactant or the reagent, you have to say the whole thing, but the potassium or the hydrogen in HCN or KCN isn't actually doing anything, and so you don't include it in the mechanism. And what will happen is the lone pair on the C, which you have to draw to get the marks, will attack this positively charged carbon. And so the lone pair of this C will form a bond with that carbon. And so what we do is you draw an arrow to show that from the lone pair to the carbon, the arrow is showing a movement of a pair of electrons. Now if that happened, that carbon atom would now be making 5 bonds. These 4 here, and also the extra bond that's just formed at the end. So something else must give. And the thing that gives is the carbon-bromine bond, because that is the one that is the weakest in terms, or not the weakest, but the bromine is most happy being a negatively charged thing. So this bond will also break, and you'll form a bromide ion. So what you make in the end is basically the same molecule, but your bromine has been substituted for a Cn-. But the negative charge obviously has disappeared because it is sharing electrons now with the C. So you've got Cn like that, and then you get Br-, which would link up with whatever the Cn- was attached to in the first place. Another thing that can act as a nucleophile and partake in this reaction is an OH- ion. So if you've watched the elimination video, you'll know that OH- can act as a base and eliminate an H and a Br from a molecule, but that's only under certain conditions. So that's when it's ethanolic and warmed, but if we use OH- in aqueous solution, so dissolved in water, and relatively cold, we can make it substitute instead. And so it does exactly the same as the Cn- did, really. So we get OH-, again what you'll have is a reagent KOH or NaOH, and it'll be aqueous and cold, but you don't draw the Na or K because then they don't partake in the reaction. You've got a lone pair on the oxygen, and that's the lone pair that will form a bond with the carbon, which, as you know, is delta positively charged, but you don't need to draw that dipole in to get the mark, so you don't necessarily have to draw it in the exam. That forms a bond with the carbon, so the bromine-carbon bond breaks, and you draw an arrow like that to show that from the bond to the bromine. Remember, the electrons in this bond are moving from between the bromine and carbon to just only on the bromine. Remember, an arrow shows the movement of a pair of electrons, so I have this lone pair here moving, or this bond here, which is also a pair of electrons moving. And that will make CCOH, an alcohol, and we could name this alcohol, this is ethanol, because there's 2 carbons of the chain. And you'll also make Br-, which again will link with whatever the OH- in the first place was linked to, or bonded to. So remember, this OH- must be aqueous for this to happen, and cold. So I'm just going to show you a short animation that shows this process happening. So I press play. So you'll see first the arrows showing the movement of the electrons, and you'll see that this is a simultaneous process. The Br- leaves and the OH joins at the same time. If we just watch that again, you'll notice the movement of the charges as well. You'll see the minus charge on the OH will disappear once it forms a bond, and the negative charge on the bromine forms once the bond is broken. Just watch that once more time. So the bond forms between the OH and the C, and the bond breaks between the C and the Br. Now we're going to do the nucleophilic substitution reaction involving ammonia and a haloalkane. And this is just a slightly more difficult mechanism to draw because there's just one more stage. Again, it's between a haloalkane. I'm going to use the same one, but as I said, that bromine that's on the carbon here can be attached to any of the carbons, and the carbon chain can be any length. And it's going to be reacting with an ammonia. Now, ammonia also has a lone pair. It's not charged, though. And this lone pair will attack the C, and the bromine will leave. Now, the result of that is two carbons with an NH3 attached to it. Now, nitrogen doesn't like making more than 3 bonds, and so that is now going to be charged. So you get this. You also get a bromide ion, which we won't draw now, and a positive charge on the nitrogen, which you must remember to draw. So this positive charge must leave in order for this molecule to be stable. And so what happens is another NH3 comes along, and that grabs one of the hydrogens, and the bond between the hydrogen and the nitrogen breaks, and the electrons go onto the nitrogen, quenching, if you like, that positive charge. And so now the nitrogen doesn't have a positive charge, and so what you make is CCNH2, one of those hydrogens is left, and it's joined onto another NH3, and what happens is that NH3 has become NH4, which would be positively charged, and that positively charged NH4 is attracted to the Br that left in the first place here. So that is now in this molecule, and this molecule is very, very stable because it's basically an ionic molecule, and the attraction between the NH4 plus and the Br minus is very strong. Now, one major problem with this mechanism, this reaction in industry, is that these two, the product here and the original reactant here, can react again to make further products, and that's because this nitrogen atom here, because it's making 3 bonds, still has a lone pair which can react again. And so what happens is nitrogen lone pair, if left, will then just react again with this carbon here. The bromine will leave, and so what you'll make is a CC attached to an N, attached to another one of these on the other side, and you'll have 2 H's still on there, be positively charged, and then another ammonia, which would still be knocking about in the solution, will come along with its lone pair, take that H, quench that positive charge, and so what you'll make is N with 1 H on it, and then 2 C2H5s either side. And then that can react again with the original molecule to make an even further substituted nitrogen atom. Now this will happen if this is just left to run in its own accord, and you can stop this happening in one way, and that is to ensure that this molecule here will bump into and react with an ammonia rather than the products that you're making. And so to stop this from happening, you need an excess of ammonia. An excess of ammonia will stop this from happening because that will ensure the probability of this bumping into an ammonia molecule is higher than this bumping into this molecule, so you'll get a far greater yield of just the product that you initially want, the product that's only been substituted once rather than more than once, like this one. So, hydrolysis is the reaction between a haloalkane and water, basically. But we can also call the reaction between a haloalkane and NaOH or KOH a hydroxide ion when it substitutes hydrolysis, because the products are the same and the reactions are very similar. But if they asked you in an exam to define hydrolysis, you would say that that is a reaction where you're breaking. So it's breaking, the breaking of carbon-halogen bonds using water. And you'll find that as you go down the group of halogens, these hydrolysis reactions get quicker and quicker. So as you go down, you get quicker hydrolysis reactions. And this is basically because, as you go down, the carbon-halogen bond becomes weaker. So if the carbon-halogen bond is weaker, it basically becomes easier to break, and therefore results in a quicker hydrolysis reaction. So let's look at a couple of past exam questions, and this is obviously going to look very similar to the slide a few minutes ago, but I want to point out where the 5 marks are for. So the first of the 5 marks is for naming this mechanism. So the question says, name and outline a mechanism for the following conversion. Outline basically just means draw. Okay, so don't be confused by that word. But name obviously means to name the mechanism, and in this case, it is called nucleophilic substitution. Which is no surprise since this whole video has been on that. So that's 1 mark. The other marks are all for the mechanism. So the first thing that I would do when drawing a mechanism to draw out all the bonds of the reactant. So there's 3 C's, the last C is bonded to a Br, and then you've got H's attached to all the C's, and it says it's reacting with ammonia. So the first step in the reaction with ammonia is NH3 bonding to the C that's attached to the bromine, and the bromine leaving. Now, basically there's a mark for each arrow and the intermediate structure, if there is any, in any mechanism question. But in order to get the mark for each arrow, you have to make sure there are certain things that you've done. So for example, the first arrow is from the N to the C, but you must make sure that you draw the lone pair on the N first. So that will be your first mark. Second mark is for drawing the arrow from the CBr bond to the Br. So there's 2 marks there. The next mark, because this mechanism does involve an intermediate, i.e. a middle step, the next mark is for the structure of the intermediate. And again, I would always draw the intermediate with all the bonds. So now you've got N attached to the C at the end, rather than the Br. So drawing all the bonds on the NH3 and all the bonds on the C. And that just ensures that if you need to draw an arrow from one of the bonds, it's not going to look messy because you've already drawn it ready to be drawn. The final step of this intermediate is to remember that your nitrogen has a positive charge, and if you miss out the positive charge, you miss that mark, and so that's your 3rd mark. And the 4th mark for the mechanism is for the final arrow. Now, remember that another NH3 comes along and grabs the hydrogen off the N on the chain of carbons, and then the electrons between the N and the hydrogen that's being taken then go in and quench that positive charge. Now actually, this bit here is not needed for the mark. The marks are for this arrow here, as long as you have the lone pair, this arrow here, as long as it's coming from the middle of the bond to the bromine, this intermediate, as long as you have the positive charge there and everything else is right, and this arrow here going from the middle of the bond from the N to the H to the N. This bit here is unnecessary, but is correct. And so you got another mark for naming, which is your 5th mark. So here's another question. So it says the student used, talking about a student that they referred to at the beginning of this question, so this is 2b, there are a couple of questions beforehand. You'll need this table from the beginning of the question to answer. So the student used the following enthalpy data to try to account for the different initial rates of reaction in the haloalkanes using part A. So here is the time taken to form a precipitate from one bromobutane and one iodobutane. So essentially this is how quickly the reactions went. The student deduced that the rate of hydrolysis of a haloalkane is influenced by the strength of the carbon-hydrogen bond in the haloalkane. State how the experimental evidence enabled the student to make this deduction. So basically the table that you got at the beginning of the question shows how long the hydrolysis reactions took to occur. Remember, a hydrolysis reaction is where you break a carbon-hydrogen bond using water in a reaction. So with one bromobutane, it took 480 seconds for the hydrolysis reaction to complete, and one iodobutane it took 15 seconds. So there is a faster reaction with one iodobutane than one bromobutane. If you compare that to the bond enthalpies, you see the carbon-iodine bond is weaker than the carbon-bromine bond. The carbon-iodine bond takes less energy, and that's basically what you have to write in your answer to get the mark. So you'd say the weaker the carbon-hydrogen bond, the faster the rate of hydrolysis. That's it. Then it asks you to state the meaning of the term nucleophile. And basically what a nucleophile does is it donates a pair of electrons. So the meaning of the term nucleophile is an electron pair donor. And that will get you the marks. This next question I chose to show you because I wanted to show you how they might give you the reactants in the mechanism. So here it says outline a mechanism. Remember, outline just means draw for the reaction of potassium cyanide with bromomethane, which is reaction 1 here. It doesn't say name the mechanism, so you don't need to do that. It's only worth 2 marks. Remember, the marks are basically for each arrow. So first draw out the molecules that are reacting. So here's the first one, CH3CH2Br. Remember, you would draw out all of the bonds. And the other thing that's reacting is KCN. Now remember back when I was drawing the mechanisms that I said you don't draw the K because it's just a spectator ion. So all you're going to draw is a CN, and the mark is for the arrow between the C in the CN and the C in between in the CBr. Remember, to get that mark you have to make sure that everything else is correct. So first it's coming from a lone pair on the C, and also this ion is negatively charged. So you must have a negative charge on the Cn-, and you must have the lone pair. The arrow comes from the lone pair to the C, and the CBr bond breaks. And those are your 2 marks. There's no need to draw the product because it's already in the question there. But you can draw it if you like. But if you do draw it, you need to make sure you get it right. If you draw it wrong, then they'll dock you marks. So that is the product there. Finally, just want to do this question with you. So explain why an excess of ammonia is needed in a reaction to produce a high yield of ethyl amine. And remember, I said you needed an excess of ammonia in order for ammonia to be reacting with the initial reactant rather than this ethyl amine product. And so what you'd say here is to prevent the ethyl amine from reacting or substituting further.